Okay, today we're talking about the Doppler effect primarily. So let's review what we did last time. We talked a little bit about waves in higher than one dimension. So in particular, we talked about waves in two dimensions, like ripples on the surface of water, or waves in three dimensions, like light emanating from a light bulb or sound from a loudspeaker, things that propagate in three-dimensional space. And we had this model of circular in two dimensions and spherical in three dimensions wavefronts that move away from the source at constant speed. So that gives rise to these wavefronts. The wavefronts correspond to the maxima or the peaks of sinusoidal waves traveling away. So let's say wavefronts in three dimensions. So we argued that in general you can write whatever is fluctuating. So if it's sound, maybe we can think about pressure or density of air. We have both pictures, we can talk about either. Or if it's light, we can think about the electric field and the magnetic field. Basically, whatever the quantity is that exhibits this wave-like propagation, at some point in space, represented by vector r, that we draw from the source of the wave to that point in space, and time t, we can write that quantity as a of r, which is a function of the distance, times sine kx minus omega t plus phi naught, kr rather, kr minus omega t, where r is just the length of that vector. We talked about the intensity at some point being the power, the total energy per unit time that's generated by the source, that's put into the system by the source, divided by the surface area of the sphere at distance r, where all of that energy is going through. So we had that expression. We introduced it, so that was intensity. We talked about phase, which is an important quantity characterizing the wave, and that's the argument of that sine function, kr minus omega t plus phi naught. We can call it phi, which is a function itself of r and t. Just as a reminder what these things were, so k was 2 pi over lambda, right? Adding a distance lambda to r adds a phase 2 pi, so that's doesn't change the sine function. You go from, for example, from peak to peak or trough to trough, and omega is 2 pi times the frequency. Okay, so we had these pictures. One thing that we didn't talk about was how a depends on r. We said, yeah, it's some function, so energy is conserved. It has to go down somehow. So the key to that is the fact that the intensity is proportional to a squared. So we kind of remember this from a harmonic oscillator, where we had energy was 1/2 k, not not that k, not the wave number, but the spring constant, times maximum displacement squared. But it's a more general phenomenon. For example, if you have an electromagnetic wave, the energy density carried by that wave goes like the fields squared. So that tells us what happens for a wave in 3 dimensions, right? So in 3 dimensions, we know that the intensity goes as 1 over r squared, so I is proportional to 1 over r squared. If you haven't seen this notation, it's kind of an elongated or stretched alpha. It means proportional to. It's a very useful notation if you don't want to worry about all the constants. So proportional to null 2. Okay. Therefore, a squared, with which itself is proportional to I, is proportional to 1 over r squared, and that means that a is proportional to 1 over r. So we can think of this wave in 3 dimensions to be some other number. Let's call it whatever you want to call it. Let's call it b over r times sine of the phase. In 2 dimensions, one expects the intensity to go down as 1 over r, right? It should go like the perimeter of that circle. So in 2 dimensions, we expect a of r to be proportional to 1 over square roots of r. That's just a side remark. So this depends on dimensionality. And in 1 dimension, of course, it's just a constant, right? It doesn't depend on distance. As you propagate in 1 dimension, you're not spreading out your energy in various directions, so the amplitude or the intensity doesn't go down, doesn't change. We talked about phase difference, which was kind of an important quantity. So thinking about this picture describing either 2D wavefronts or the projections of a 3D spherical wavefront on some plane. And the distances between these were lambda, were the wavelength. So we managed to find the phase difference between different points, right? So we would see what distance they are from the origin, from the source of these waves. And so let's say you have one point at distance r1, you have another point at distance r2. The phase difference is simply r2 minus r1 times or divided by lambda times 2 pi. That's what one gets from just subtracting these two phases, because if we're considering the phase at one instant of time, then omega t minus omega t plus phi naught, they just cancel out. And then we're left with k times r2 minus r1, and k, the wave number, is 2 pi over lambda. All right. So we also introduced the concept of decibel. It's just a convenient way to describe the loudness or intensity of sound waves, and we had a little bit of practice getting the decibel from the intensity. All right. So before starting the discussion of the Doppler effect, let me work out one example, and then we talk about the Doppler effect. Okay, so here's the example we want to work out. So let's read through this, and please then pause the video, try to find the solution. So we have a sound source that's on the x-axis, and the same wavefront reaches two listeners, one on the x-axis, one at x equal -7 meters, the other at x equal +3 meters at the same time. So these are on the x-axis. So part A is asking where is the source, and part B is asking if you have a third listener on the y-axis, where is she on the y-axis if the same wavefront reached her at the same time as it reached the first two listeners at x equal -7 and +3 meters. All right, so pause the video, try to find the solution to this. All right, so what do we know? So if a wavefront reaches some listeners or observers, well, these listeners must be on a circle whose center is the source, right? So let's think about the x-axis here. So x, y. So you have one listener at +3 somewhere here. You have another at -7, maybe somewhere here. And then you want to see where the source is. Well, so if the source is somewhere on the x-axis, which is what the problem is saying, it must be the same distance from these two listeners, right? They are on a circle, right, whose center is the source. So this must be the radius of the circle, and that must be the radius of the circle. So the distance between the two must be twice the radius. Okay, so if that's -7, that's +3, that length is 10. So from here to here we have 5 meters. From here to here we have also 5 meters. So therefore, let's say 3 minus 5, we can find it to be -2 meters. Or you can do -7 plus 5 again, gives -2. Okay, so that was easy. And then having this geometric picture, again, makes it easy to find where is this third listener on the y-axis. Well, there are 2 points, right, on the y-axis, here and here, where this circular wavefront hits the y-axis. Okay, so how do we find it? How do we find the distance? Well, we know the radius, right? So let me draw a picture again. The x and the y-axis. So I know if that's the source, right, from here to here, I have 2 meters, right? The source we just found is at -2. We know the radius is 5. So from here to here, I have 5. So this length should be square root of 5 squared minus 2 squared, right? 5 squared minus 2 squared, that's square root of 25 minus 4 is 21 meters, whatever that is. So then the third listener can be at plus or minus, right? It can be on either side of the x-axis. 21, square root of 21 meters. You can put that into a calculator. It's 4 point something. All right. So now let's begin talking about the Doppler effect. And Doppler effect is an extremely important phenomenon in physics. It appears in many different contexts. So a very familiar example is like a car or a motorcycle or something that's making a noise, especially if there's a siren or something, just passing you, right? If it's moving toward you, you hear some kind of sound. And then when it just moves past you and is moving away, it seems the pitch of the sound changes. We hear a different pitch. So there's something about sources that are moving with respect to observers or listeners. It's quite important in astronomy. So again, the light emitting from distant stars or galaxies, depending on how they move, the frequency should change. We see a different color if it's in the visible range, for example. So we can learn about the expansion of the universe from this phenomenon. In many other areas of physics, so for example, another area, it's used, for example, in cooling atoms with lasers. So you can shine lasers, you can shine light on atoms. And these atoms, depending on whether they're moving toward the laser or away from it, from the point of view of the atom, that light has a different frequency. They see different frequencies. And then, atoms have some natural frequencies, some resonances for absorbing energy. So one can tune these things. So if the atom is moving toward the light, toward the laser, it absorbs the light, and then it just slows it down because it's being hit like head on with the light, and light has momentum. So it slows it down, whereas when it's moving away, it's not absorbing that light because there's no resonance. It's seeing different frequencies. There are other applications of the Doppler effect. For example, radar is a classic example. It's used in weather stations, for example, determining, for example, how fast the wind is blowing. Police cars catching speeders. And also there are some medical imaging applications. I think there are these Doppler ultrasounds which can detect like how fast blood is flowing, for example. So it's a very it's an important phenomenon that has found many applications, both for sound waves and lights. All right, so what's the story? Well, the idea is we have an observer. So let's say here there's an observer. And you have a source, let's say a loudspeaker, so a source of sound, that is moving. So at some instant of time it's here, a little bit later it's here, right? The source is moving source. Okay, so we quite well understand the behavior of a stationary source, right? It keeps putting these wave fronts that propagate away at the speed of sound, or at the speed of the wave propagation, whatever that wave is. Now, so what happens if the source is moving? So let's try to draw a movie together. Let's see what's happening. So let's say initially the source is here, and it puts out, let's say, a wavefront at that point. Okay. And a little bit later, so what happens is that wavefront, it originated from that point, right? So once these disturbances leave the source, they they start propagating in the medium, they become pressure waves in the air, they couldn't care less where the source moves later. So as far as that disturbance, that first wave front is concerned, it originated from the initial position of the source. So it's going to be somewhere over here. However, at the same time, the source has moved, so the source is no longer there. The source is maybe somewhere over here. It's moved forward a little bit. Okay? Now, so let's say t equals 0, t equals delta t. Some time has passed, and in that time, the source moves at a certain distance. And the wavefront propagates by some distance. Okay. So then this, let's say this time corresponds to one full period of the oscillator. So then the source is put in the next wavefront at this point. And then, so what happens is in the time that, let's say that the source moves forward even more, now this original wavefront has grown, and then there's another wavefront whose center is this point, the previous point. So there's going to be a bigger wavefront over here. And another wavefront around this point. So see what's happening, right? So it seems that as the source is moving this way to the right, the distances between consecutive wavefronts in front of it on this side get shorter, they get compressed together, they get squished together. However, in the back, the distances seem to grow, right? So from the point of view of an observer who's just standing there being hit by these wavefronts, the wavelength that this observer experiences is the distances between these wavefronts that reach her, right? So from the point of view of this observer, the wavelength has shortened. And an observer over here will see a longer wavelength, right? So let me show you a better picture. My drawing skills aren't very impressive when it comes to circles, especially. So let's see. Let's try to draw that picture better. Okay, so that's a better picture. So let's say initially the source is here, so that's the original wavefront. And in the time that this wavefront has grown by this much, the source has moved all the way from 0 to 3. At point 1, again, it generated a wavefront that has now reached this circle. When the source reached point 2, it generated this wavefront. So over here, we see these wavefronts compressed together. So that's what Nancy sees over here. And Pablo, who's standing behind this source that's moving away from him, sees this longer wavelength. Okay. So how can we work out the math here. So what are these wavelengths, right? So the wavelength that this source would produce if it were stationary is lambda, right? So this one has distance lambda, would be lambda naught, let's say. So this wavefront has radius lambda naught, this one has radius 2 lambda naught, 3 lambda naught, etc. So it basically reduces to a geometry problem. We want to find this distance in front and this distance in the back. And we know two things, right? We know the speed of propagation of sound in the air or in the medium. We also know the speed of the source. We know how fast the source is moving. Let's try to find those two effective wavelengths. So one way to do it is to just consider two wavefronts. So let's for now forget about the source moving, right? So let's think about a stationary source. And consider two wavefronts. One circular wavefront, another circular wavefront. Right, so the source is oscillating with period t, capital T, right? And then these waves propagate at the speed of propagation in the medium, let's say the speed of sound. So let's imagine the first wavefront has been propagating for a time, let's say t plus capital T, and this one has been propagating for a time t. Right, if their distance between them is lambda, we know lambda is Vt. So two consecutive wavefronts separated by one wavelength have propagated by the difference between their propagation time is the period, is capital T. Okay. So now what happens if the source is moving with velocity, let's say Vs, V source. So let's say it's when we start the clock, that's when this outer wavefront originated. So that one's gonna be the same, right? So let me just write right below. Okay, so that's the position of the source when this wavefront was emitted. But then the next one must have been emitted at a time capital T later, right? Therefore, it's been propagating for a time small t that's less than the time this one has been propagating by capital T. So over that time period, now the source has moved the distance t times Vs forward, right? So then we would see a circle of the same size, same radius. The radius is going to be, if you wish, for this one it's V times T, and for this one it's V times T plus capital T, which is V times T plus lambda, right? That's why they differ by lambda. Now we're interested in this distance over here. So an observer or a listener right there, that shorter distance is the wavelength she would perceive. And what is that? It's just, you see, the whole thing is shifted. The inner circle is shifted forward by t times this effective lambda we call lambda plus. We call it lambda plus because when the wavelength gets smaller, the frequency goes up, and we mainly think about frequency. So this is going to be lambda, let's call this lambda naught, right? The original frequency, the original wavelength for a stationary source, minus Vs, the velocity of the source, times t. However, t, the period, you can also think about it as lambda naught divided by v, the speed of propagation in air. So putting this into that gives us lambda plus is equal to lambda naught minus Vs over V times lambda naught. So this becomes lambda naught, if I factor it out, 1 minus Vs over V. Similarly, over here, an observer or listener that's standing behind, so the source is moving away from him, perceives a longer wavelength, lambda minus, which is similarly given by lambda minus, is lambda naught minus how much the source has moved, Vs times t, plus, right? So if that circle is shifted forward, it adds to the separation between wavefronts. So that's going to be lambda naught plus Vs lambda naught over V. So we find lambda minus is lambda naught 1 plus Vs over V. Okay, so we found these relationships. Let me repeat them here. Lambda plus is lambda naught, the wavelength the source would create if it were not moving, times 1 minus Vs over V. Vs is again speed of source, and V is speed of sound or speed of wave in the medium, and lambda minus is lambda naught 1 plus Vs over V. Okay, so now we can think about the frequencies associated with these. So we know that that the speed of propagation in the medium is constant, is V. So the perceived frequencies will be related to these perceived wavelengths as follows, right? So we will have F plus, the frequency over here, is going to be V over lambda plus, and similarly F minus, the frequency perceived by a listener from whom the source is moving away, to be V divided by lambda minus. So this we can write as V lambda naught 1 minus Vs over V. This we can write as V over lambda naught 1 plus Vs over V. And of course, V over lambda naught is the frequency of the source, right? So that source, if it were stationary, it would generate a wavelength lambda naught when the speed of propagation is v. So that's just f naught source frequency. Here we get 1 minus Vs over V. Here we get 1 plus Vs over V. All right. So that was an elementary derivation of the Doppler effect. So let's try to think a little bit more about this. As we said here, we perceive a higher frequency, shorter wavelength. Here, smaller frequency, longer wavelength. So yeah, so that's just a review of what we discussed. In words, so yeah, so we just if, for example, a source approaches Nancy, she detects a frequency that's slightly higher than the natural frequency, and as long as the velocity of the source doesn't change, as long as it moves at a constant speed, this frequency does not change with time. And similarly, if the source moves away, again, there's a there's a lower frequency, and it doesn't change with time as long as the speed of the source is constant. Okay, so these are the formulas we just derived, right? Stationary observers, and the source that moves at constant speed Vs, and V is the speed of propagation in air. There's another way to think about the Doppler effect, and that's when the source isn't moving, right, but the observer is moving. So instead of the source approaching you, maybe you're running toward the source. So they're closely related formulas. So in this case, VO is the speed of the observer, and V again is the speed of sound. So let's think a little bit about this as well. So let's say observer moving, let's say toward the source. So what's happened? So the source is here, it's stationary, and we have these concentric wave fronts, right? The distance between them is lambda naught. And now the observer, let's say at the time when this wavefront reaches her is over here, so observer, source. Now, if the observer were not moving, right, it's gonna take a time, capital T again, for this inner wavefront to reach her, okay? But now, what's happening? So this observer is moving this way with V naught. This wavefront is moving this way with speed V. So how long is it gonna take? Well, the relative velocity is V plus V naught, right? So both of them are moving together. So let's say that distance is lambda. So now let's say there's going to be a time t plus for this second wavefront to reach the observer. So what we can write is lambda is V naught plus V times t plus, the time between two consecutive wavefronts. So how does it relate to the frequency, well, the frequency is just going to be 1 over that. So this is V naught plus V 1 over F plus, the frequency that this observer perceives. And that has to do with the pitch of the sound. So higher frequency sounds are more high pitched. And lambda, as usual, is also V over F naught, the frequency of the source. So from this we find this is again equal to V naught plus V over F plus. So what do we get? So we get F plus is F naught times this divided by V, which gives me 1 plus V naught over V. And similarly, if the observer is moving away, the only thing that changes is here the sign of V observer changes, right? So we find V F minus if the observer is moving this way with V observer becomes F naught 1 minus V observer over V. So we looked at 2 different scenarios. One is the source is moving either toward an observer or away from the observer. In the second scenario, the observer is moving either toward the source or away from the source. And in both cases, we found expressions for the frequency observed by the observer or perceived by the observer. In this case, as a function of the frequency of the source, the speed of the source, the speed of sound propagation in air, in the medium. In this case, as a function of the speed of the observer, and of course the speed of sound propagation and the frequency of the source. So these are important relationships for the Doppler effect, especially with regards to sound. Okay, so a little bit later we'll talk about the Doppler effect for light, and it turns out we can't use the same derivation for light because light moves at the speed of light, which is really fast, and kind of this classical mechanics or classical kinematics picture is not adequate. We have to use the theory of relativity, which is not something we're doing in this course. So I won't be deriving the expressions for the Doppler effect for light. We'll just take them and use them. They're going to be a little bit different from these expressions here. But just as a word of caution, we just cannot, let's say, replace the speed of wave propagation v in these expressions with c, the speed of light, and expect that to work. In the regime of things moving fast, comparable to the speed of light, Newtonian mechanics doesn't work. We have to use the theory of relativity, and things change a little bit. I mean, change actually fundamentally, but in terms of the equations, the equations change a bit. And we won't be deriving those, but we need to be careful not to use the wrong equations when we talk about light. All right, so let's have a quick check problem here. So pause the video, think a little bit about this, and then we'll discuss it together. Okay, so let's think about this. So we have a siren that emits a sound wave with frequency f0. And this graph shows the frequency you hear as you stand at rest at x equal 0 on the x-axis. So you're standing on the origin. And the question is, which is the correct description of the siren's motion? So basically, like, we are at rest. The siren is moving, the source is moving. And before t equal 2 seconds, we hear a smaller frequency than the source frequency, than the natural frequency of the source. After that, we hear a larger frequency, right? So the frequency we hear is initially less than f0, and then after 2 seconds is larger than f0. Okay, so what does it mean? So if the frequency is initially less, it must mean that the siren is moving away from you, right? If the source is moving away from you, you hear a smaller frequency. And if that frequency is larger than f0, it means it's moving toward you. So here, before t equals 2, it must be moving away. Here, it must be moving toward. Okay. So first, it moves from left to right and passes you at 2 seconds. So that means previously when it passes you, before passing you, it's moving toward you, and then it's after it passes you, it's moving away. So that doesn't work, right? That would do the opposite. We want it to be first moving away, and then after t equals 2 seconds moving toward you, so you hear a higher frequency. Moves from right to left, passes you. Again, it doesn't matter. The direction is irrelevant, right? Again, first it's moving toward you, then it's moving away. That doesn't work. C says it moves toward you for 2 seconds, but doesn't reach you, then reverses direction. Again, it's first moving toward you, then moving away. So D is the correct answer. It's moving away from you, therefore you're hearing a lower frequency, then it reverses direction and moves toward you, but doesn't reach you. So D is the correct answer. Okay, that's a good place to stop, and we'll continue talking about waves and the Doppler effects for light in particular in the next lecture.